Ammonia. Manufacture of ammonia. Haber process. Nitrogen plus hydrogen give ammonia. Look this equation. This is a double arrow. So this can be an equilibrium. So the early rule, Le Chatelier principle, will apply. Look onto the gas. The ratio is 4 to the product of 2. Means you can be affected by the pressure. Higher the pressure favor the small number. Lower the pressure favor the bigger number. Look onto the temperature. This is an exothermic reaction. So, when you apply heat, you increase heat, you will go towards the reactant. When you reduce heat, it gives you more product. So, pay attention. This equation would perfectly fit onto the Le Chatelier principle. And most ammonia used as for fertilizer. Other use, for example, like you heard some household ammonia. That's very good for cleaning. And ammonia, they also can use it to make explosive and other like refrigerant or pharmaceutical. Plant need nitrogen compound to make protein and DNA for its growth. If the plant don't have enough nitrogen compound, the plant will grow very slow. And this nitrogen compound, if you look onto a DNA and look at the protein, you find in that molecule they have a lot of N atom in it, this nitrogen. And nitrogen in the air are quite plentiful. 80% in the atmosphere is nitrogen. Can we use it? No. Nitrogen, they are a triple bond. They are very stable and unreactive element. The triple bond is very strong and hard to break. And plant cannot break this triple bond to make it for its own use, for its need. So, this triple bond is too hard to be broken. And they will have, it requires a very, very high activation energy to break this triple bond to make it into any usable product. As in the usable product like ammonium, nitrate, or urea, all that will be the useful for the product. And the farmer, in the olden day, they relying on the soil bacteria. The soil bacteria have the nitrogen fixing bacteria that they can fix nitrogen. And so, olden day, they need to have a crops rotation so that to make sure the farmland have enough nitrogen going around for the plant growth. But today, we rely heavily on Haber process, this nitrogen fixing technique, so that for enough nitrogen for the fertilizer. In World War I, Germany in war with allied country, Britain and France. And Germany, they rely heavily on import of nitrate from Chile. And for the purpose for the farming and to make explosive for the war, this nitrate. An airline, he tried to block German access to Chile for this nitrate board product by he put in the battleship. So now German cannot access to the Chile, so he cannot make explosive. And Britain and France say, well, the war they're going to win over. But there is a turnaround point, and the scientist Haber, he synthesizes ammonia through another way, an alternative route to access nitrate. So now this war was continued for another 10 years. Now let's look on to the discovery of making ammonia. Look onto the equation. Fritz Haber, German scientist, in 1905, he published nitrogen and hydrogen gas under iron catalyst at 1000 degrees. It can produce ammonia, and he won the Nobel Prize. Pay attention, you require 1000 degrees. What is 1000 degrees mean? Very high temperature. If you think about the melting point of copper, 600 to 800, iron 1200, 1000 degrees to heating a gas. This experiment is a very expensive and is not easy to achieve experiment. And yes, he does succeed to make small amount only. And so this is a laboratory success. Can he make a mass production? No way. Too much energy, too little product. But he won the Nobel Prize that because it does succeed in making it. Then Carl Bosch, another German scientist, he using the same equation, nitrogen, hydrogen gas under the iron catalyst. But this time, he only need 500 degrees. And with pressure. So you will think, how come 500 degrees make much difference? Yes, 500 degrees is much lower temperature, and many containers can easy to sustain and can contain 500 degree gas, but not 1000. And the trick of it is not only the temperature, but it's the pressure that Haber did not put attention to, because he only using temperature and without looking onto the pressure. Now, under the Le Chatelier principle, now let's examine. This is an exothermic reaction. So, if you want to have more product, in fact, you should lower the temperature to give you more product. Look onto the ratio, reactant 4, product 2. So you need high pressure to give you more product. So Carl Bosch, by this technique, he not only to make small amount, but he can make into a big amount. So for this laboratory process success, now he can make it into a big industrial production. Look onto this equation, ammonia. Let's look onto the graph. This graph has 3 parts. X-axis, pressure. You can see here the pressure is increasing. The pressure, kPa. y-axis, the percentage of product, how much ammonia you can achieve. I didn't write 100 because you never achieve 100% product of ammonia. And that's another factor, temperature, different degree, 600, 500, 400. Now, let's look one by one. Let's examine the pressure, about high pressure room. As according to Le Chatelier principle, this ratio are 4 to 2. You want to go to the less number, you need high pressure, and it will give you more product. So, then you say, so you can see on the graph, the overall trend, they all favor higher pressure, give more product. The higher the pressure, the more product. The higher the pressure, the more product. Then why we settle in the middle? But too high pressure, with the vessel may not be able to sustain. As example here, if there is a pressure required, you need to have a thicker wall for the container. What happens if the pressure increased? You need to have a thicker and thicker wall. What happens more pressure increase? You need to have another thicker and thicker wall. Now it starts to be impractical and unrealistic. So, in order to produce a reasonable amount of product and about 350 atm, this is a good pressure that the vessel will be able to sustain. Now let's look on to the temperature. Low temperature, because it is exothermic. The heat. So, in order to give you higher yield of product, you need to lower the temperature because this is an exothermic reaction. So, if you look onto this graph, you will see if you put on 600 degree temperature, high temperature, it only gives you about 10 to 20% product. It's very low. 500 degree, it gives you about 30%. If you lower the temperature, which will even less energy, 400 degree, it can give you about almost 50% product. So why not? Less energy and more product. But one factor we did not consider. Low temperature is high yield, but they're slow. In this graph, you only mention about the pressure factor and the temperature factor. And we did not mention about the timing factor. In fact, on high temperature, 600 degree, the reaction are quite fast. In low temperature, 400 degree, they give high production, but they're too slow. It takes hours of production. So, in order to produce a reasonable amount of product, we're taking 500 degree. And in this reaction, iron oxide as a catalyst we always require. And the use of catalyst is to increase the rate of reaction. But it will not help you to get more product. It will just make it too faster to reach to the equilibrium level. So when you monitoring, if you are a chemical engineer, you have to an important role to ensure this plant functioning efficiently, economically, and safely. So how you going to get a maximum production? We consider in three parts: input, process, and output. Input. Your ratio, hydrogen gas and nitrogen gas, always 3:1 ratio. If you don't put it into this ratio, and soon you will slow down the production. Second, the material must be pure. You cannot let any other compound in, because at 500 degrees with catalyst, any other compound will have an unwanted reaction. If you have oxygen go in, explosion. Carbon go in, you will form into a different product. Process. You have to control the temperature we mentioned, control the pressure we mentioned, and the catalyst. Output. In order to increase the product, Le Chatelier principle say you should constantly remove the product so that you will have more product to produce. And remember, the maximum of your production is around about 35%-ish. Another 60%-ish is still unreacted, because this is it is an equilibrium. And what you're going to do with those unreacted, you should recycle it. So this is the Haber process of the production.